And the formula for it is this. A adjoint inverse is equal to A inverse adjoint. So I think, I mean, you can do, this is kind of a twofer in terms of the proof. Like, if you can prove that this, if you can, basically, if you could show that A inverse adjoint times A adjoint is equal to the identity, I think that would essentially give you a proof, right? I mean,
Yeah.
so I think, as is with everything here, he does that, well, you know, he says it suffices to show that A inverse adjoint times A adjoint X is equal to A adjoint times A inverse adjoint X is equal to X, right? So you do need both the left and the right multiples working like this for every X and H. And let's see here. So what he does is he just looks at the inner product of Y with A inverse adjoint A adjoint X and first of all he brings the A inverse back to the other one, right? And then what's he do next here? And then he brings the A back, right? A, oh, look at that. But that's why. So yeah, I think I've written enough for this one. So that's half of the proof essentially. So what you've shown at this point, right, is that this, since this holds for all y, it follows that this is equal to that, which gives us that, right? And so essentially the same calculation goes through. If you look at the other one, it's just that you get your A first and your A inverse second. But A inverse A is also equal to the identity because we're assuming A is invertible. So anyway, that's, I sometimes ask this in the finite dimensional context of my linear algebra. I'll tell you what, that'll mess some students. It messed me up at one point. I don't know why. It's just for some reason it's easy to get your, when you like, it's easy enough to believe it, but when you ask yourself how do you prove it, it gets, I don't know, it gets me some days. It shouldn't. It's really not complicated, but anyway. And then corollary to this, if you have a bounded self-adjoint operator, has bounded A inverse, then A inverse is what? Here, let's do the proof here. So we have A inverse conjugate, adjoint, equals to, according to the theorem, A adjoint inverse, right? But it's self-adjoint, right? So that's equal to A inverse. So what does that show about A inverse? A inverse is? Yeah. There you go. That brings us to our next definition of what's called a normal operator. Bounded operator T is normal operator if it commutes with its adjoint. T star is equal to T star T. Now, so obviously, what's one thing you can tell me immediately about that? So let's see, how about as a self-adjoint? My question is, what do you think? Is a self-adjoint operator normal? Yeah. Right, yeah. So clearly a self-adjoint operator will be normal because it's very silly. So T stars T is TT. Yeah. So yeah, self-adjoint implies normal. The converse is not true. Don't make me give you an example, but there are operators which are normal but not self-adjoint. All right. Normal operators have properties that we like this could serve as a definition. So you could say that a normal operator is one for which the norm of Tx is equal to the norm of the adjoint of x for all x. So that's one thing you could use as a theorem. I mean, you could use it as a definition if you wanted to there. All right. I will forego the proof of that if you guys don't mind. He points out that some nice examples. So, well, actually, I should give you some examples of operators which are not self-adjoint, but nevertheless are normal, because these are important examples and they're easy. That's actually his next example. So, examples of normal but not self-adjoint. So I think he says let T be self-adjoint. All right. So let T be self-adjoint. I think that's what he says. Oh, no. That's not it at all. My bad. He says let T of x equal to Ix. Or and then his point is that the adjoint of T x is equal to minus Ix, right? Which is not equal to, which is equal to minus Tx, right? So, in fact, the adjoint of T is equal to minus T here. So this would sometimes be called anti-self-adjoint in sort of physics-y stuff. But obviously, it's still normal, right? Because if you use the last theorem, if T star is minus T, the norm eats the minus. Yeah. All right, next theorem. trying to make the most of the day. So don't worry, I won't go too long. My wife has requested I come home at some point. So if A is normal, then if A is normal, then you can do a scalar multiple of the identity operator minus A, I think he says, is normal for all alpha in the complexes. Actually, that's kind of surprising. Why is that true? Oh, I see why it's true. So if you look at alpha, yeah, so if we do this times alpha I minus A, what do we get? We get alpha conjugate I minus A conjugate, conjugate.
Oh, right, yeah.
The adjoint of the identity is the identity. That's a property. At the start of the section, it's probably a homework problem for you guys. But of course, then we get, so I'll write it out. So we have alpha, yeah, modulus of alpha, but that's alpha II, minus alpha bar A, minus alpha A conjugate. And I'm not writing the I because, whatever. And then plus A conjugate A. And the thing is, you could just as well have written the other way. The reason that those are equal, there's the critical thing that you need here is that A is that's equal to A star, which is what follows from the normality of A. Yeah. And of course, we also need to flip the order of the multiplication, but those are numbers, and the addition comes out. And depending on how you distribute things, it could look different. But addition commutes, so there you go. All right, great. Let's see here, theorem. Let T be a bounded operator in a Hilbert space. Let A and B be the self-adjoint operators which decompose T. Then T is normal if and only if A and B commute. Ooh, interesting. So theorem. T, I'll just write the interesting part. T equals A plus IB. All right, then T star equals T star T if and only if AB equals to BA. Now here, of course, we're talking about A and B being the unique self-adjoint operators that decompose the T, as we talked about in the theorem earlier today, right? Oh, I've got to look at the calculation for this one. Hopefully I won't get in trouble. Let's see here. Let's see, A plus IB, right? And then A plus IB adjoint. And then by properties of the adjoint, we've got A plus IB times A minus IB. And you're right, it would be adjoint, but A and B are self-adjoint, so I'm just dropping them. And, oh, well, duh. Well, duh, yeah. So that's AA minus IAB plus IBA minus I squared B squared, which is equal to A minus IBA plus IAB minus I squared B squared, which is A minus IB times A plus IB. So what I did here is this step is only true for AB equal to BA. More to the point, if A and B commute, you can commute these. But commuting these is tantamount to getting A plus IB adjoint to commute with A plus IB, which is to say that T star is equal to T star T, which is to say, of course, that T is normal. So it's this calculation with a little bit more window dressing, yeah. Ooh, theorem. See, normal operators are awesome. They have like really cool properties, like this one. The norm of T to the N is equal to? That's right. Exactly, that's how it works. Yeah. Which brings us to our next. Yeah, so the spectral theorem of linear algebra. So like one of the, as this impacts real linear algebra, the theorem that it shows up in is this one. The basis for a, if you have a symmetric matrix, there exists a orthonormal eigenbasis. And moreover, all of the eigenvalues are real. So this technology, these normal operators and adjoint operators, they're used in the proof of the spectral theorem. And, but that's just, I'm just talking finite dimensional. I think that this book, though, will have the infinite dimensional analog to that. So I'm looking forward to it. It's a little bit later. I mean, that ties into the projection stuff that's coming up. Probably not today. A bounded operator on a Hilbert space. Yeah. So a bounded operator on H is called an isometric operator. If the T of x is equal to x for all x. So an isometric operator is one which preserves the norm. And he gives an interesting example of such a thing on a Hilbert space with a complete orthonormal sequence. So his example it's kind of a interesting example. If you have a complete orthonormal sequence in a Hilbert space H, all right? Yeah, I think this would be a separable Hilbert space. He says, then there exists a unique operator, A, such that A of En is equal to En plus 1 for all n. Yeah, like a ladder operator in physics. Physicists, mathematicians always call these things shift operators, but you're right, we do call them ladder operators in physics. Man, that takes me back. Yeah. And so, in particular, he's like, if you have x is equal to the sum alpha n En, right? Then AX, right? Then AX is what? Well, it's the sum n equals 1 to infinity of alpha n e sub n plus 1, right? But remember, how did we calculate the norm in such a separable Hilbert space? It's just the, square root sums of the alpha n, well, these guys, I believe, right? You're fine. So the point is, even though it's like, it has exactly the same coefficients, it's just they're shifted one over, but it doesn't like over count or anything. I mean, but this is of course equal to.
Okay, yeah.
So A is isometric. I mean, it's very sneaky. He said this is called a one-sided shift operator. And so there's a theorem about these guys, and this will also be very reminiscent of physics once I put it up here. The theorem is this: a bounded operator T on a Hilbert space H bounded T on H, Hilbert space, of course, is isometric if and only if T star T is equal to the identity on H. So, all right, so the proof of this, let's see here. So, if the norm of Tx, right, is equal to the norm of x for all x in H, then what do we get? We got the inner product of Tx with Tx, right, is equal to the inner product of x with x for all x. Which then gives me that the inner product of x with T star Tx is equal to x with x for all x in H. Thus, T star T is equal to the identity but the norm of T star x is equal to the norm of T x. That's a general identity for any bounded operator. So this is also equal to the norm of x. And so by a similar calculation, we get T star is equal to I, right? Basically, you can run through the same calculation. I mean, because I have this is equal to this, that puts star here, which puts the star in the opposite order. And therefore, that implies then that implies, so we have this. I guess I didn't need to prove that, though.
Yeah.
Huh. Well, anyway, it's true. And, well, that's good, because if you have, if you have both this and that, this together makes,
I think we're assuming that's normal.
T is called unitary. If T adjoint T equals to I equals to T adjoint. What's that?
I was looking at theory 5.8. Now I said the norm of T star X equals norm of TX. That already assuming that T is normal, then they were going to say that last part. Because we haven't size seen that.
Oh, you're right. We don't have that it's normal, so I can't do that.
Yeah.
Oh, I'm sorry. Oh, yeah. My bad. You're right. That is not a general operator identity. Yeah, don't buy what I'm selling. It's not true. So, okay. So yeah, apparently this does not automatically come for free.
Unfortunately.
Aw, man. Okay. Well, anyway. Sorry about that. But we did get the T stars T equals to I that we wanted. And then if we go the converse direction, right, if we assume that T star T is equal to I,
Yeah, we can just do the same thing, I guess. So that
then we can reverse.
it's our norm, so
So we can reverse the calculation in that.
the square root of the norm of TX equals the square root of inner product XX, so the norm of TX.
For all x and I, good job though. For all x and h, maybe? Okay, so yeah, and then his definition is T is a unitary operator if T star T is equal to I and it's equal to T star. That's the definition of a unitary operator. Theorem, an operator T is unitary if and only if it's invertible. T unitary if and only if T inverse exists and T inverse is equal to T star. Right? That's almost immediate from the definition if you look at it. I mean, see, if it's unitary, you have this equation, but that equation is tantamount to the existence of an inverse
Yeah.
for T, and that inverse has to be the adjoint. So it's,
Right. Yeah.
this theorem is a hop, a skip, and a jump away from the definition. I mean, it's, who says that? What's wrong with me? Schoolgirl? Good grief. Yep. And then, ooh, what the what? Let H be the Hilbert space of all sequences of complex numbers. Ooh, that's not a sequence as I ever define it. Funky.
But, I thought sequences mapped just from the naturals.
Yeah, so this is, I think some people will call these double sequences.
Oh.
You know, it goes infinity both. It doesn't have a start. So example, H equals, basically you're looking at X that are mappings from the integers to the complex numbers, right? Such that the sum n equals minus infinity to infinity of the absolute value of xn. Is it squared? Squared, isn't it?
Yes. Yes.
So that's a new space. No, you're fine. Don't worry about it. It also gives me a chance to check on my time. Oh, we're an hour and a half right now. I better wrap it up pretty soon. I know your brain's probably a little bit toasted already from the MFAT, right? I'm just kidding. That's actually kind of relaxing, isn't it? But so
It's called double sequence.
yeah, I think I've heard these called doubled sequences before, and then the inner product on this space is defined the way you'd expect, right? It's just like the sum minus infinity to infinity of, you know, xn, yn conjugate. And so he defines t of x well, he uses this notation, t of xn equals to the sequence xn minus 1. So it's a shift, infinite shift, and so it's invertible. What's the inverse?
I'm guessing it's going to be xn plus 1.
I think that's right. So it's an infinite. So it's invertible, and he says it's in fact a unitary operator, and it is in fact unitary because you can. Well, we can try it out. Let's see, txy equals the sum minus infinity to infinity of what? X n minus 1 yn conjugate, right? But if you let k equal n minus 1, then n equals to k plus 1. So re-indexing, we've got x sub k, y sub k plus 1 conjugate, which of course is x sub k t inverse of y conjugate, which is of course the inner product of x with t inverse of y. So therefore t inverse is equal to t adjoint. Consequently, unitary. Of course, once you understand what the inner product here is, the fact that this is unitary is just kind of in your face, like, of course it is. The length is preserved. I mean, this is what a unitary operator is really. It's a length preserving map. So unitary operators, in the context of Euclidean space, they're the orthogonal operators. So when you think unitary, you can think complex orthogonal. Let's see here. He says, let T be a unitary operator, then T inverse and T star are also unitary. So like if theorem T unitary, T inverse and T star also unitary. So that's the final theorem for this section, 4.5. Let's see here. I'm very tempted to skip a couple sections here and just skip over to eigenvalues and eigenvectors next time and see if it's too horrible for us to do this. I mean, technically speaking, I'm skipping the section on, well, in terms of the analysis, I'm doing the most violence because I would be skipping the section on compact operators. Projection operators and positive. So the positive operator section I'm the least bothered by skipping because, like I said, the positive operator section is essentially asking the question, can you find the square root of an operator? And the answer is, yeah, sort of, kind of, sometimes. Ultimately, answered in his final theorem, square root. Well, no, his definition, square root of a positive operator, self-adjoint operator B satisfying B squared equals to A. No surprises there. And then theorem 4.6.14, every positive operator A has a unique positive square root B. Moreover, B commutes with every operator commuting with A. So, yeah, so the definition of positive operator given in this section is a self-serving definition to make this, theorem happen. It is a definition given so that the square root of an operator exists. So, I don't know. And I guess the definition isn't too unnatural either. Like his definition of positive operator. Operator is called positive if it's self-adjoint and the inner product of AX with X is greater than or equal to 0 for all X. So, okay, whatever. Projection operator section is perhaps more interesting, but I don't think it'll be too bad for us to skip it. I'm a little bit more concerned with the compact operators just in terms of like, am I cheating you guys by not talking about those things? The compact operator is, anytime you talk about compactness, you're talking about some idea of finiteness, all right? So like his definition of compact operator, an operator A on a Hilbert space is called a compact operator or completely continuous operator if for every bounded sequence, the image of that sequence under the operator contains a convergent subsequence. So, for example, every operator on a finite dimensional Hilbert space is compact. All right, so, and he's got some nice theorems in this section, like the collection of all compact operators on a Hilbert space is a vector space, or if you have a compact operator in a Hilbert space and B is a bounded operator on H, then A and B and A are compact. So like, even when A is not, oh, wait a minute. Okay, so the product of a compact operator and a bounded operator is compact. Either way, A, B, or B, A. And, the projection operator is a compact operator if it's the projection onto a finite dimensional subspace. He defines a finite dimensional operator as being basically an operator whose range is a finite dimension. He's got this theorem 4.8.12, the limit of a uniformly convergent sequence of compact operators is compact. And it's got this epsilon over 3 argument that you always see with the uniformly continuous things. So that's kind of neat. Corollary, the limit of a convergent sequence of finite dimensional operators is a compact operator. It's nice. The adjoint of a compact operator is compact. And then his theorem 4.8.15, it says that a compact operator turns weakly convergent sequences into strongly convergent sequences. So, and that actually is a little bit technical. And then finally, a corollary, compact operators map orthonormal sequences into sequences strongly convergent to 0. That sounds like it might be useful. Let's see here. Proof is online. Whoa.
No, one line.
Oh, one line. Okay. The proof is online is very different. Let's see here. Let's see here. He says, compactness of operators is a stronger type of continuity. For this reason, compact operators are sometimes called completely continuous operator. He says this condition has been used by Reitz as his definition of compact operators, and Hilbert had still another equivalent definition of compact operator, which is involving the inner product. So yeah, I think I'm just going to be content for us to read it together like we just did, and we'll go on to eigenvalues and eigenvectors next time. Which I think will be interesting. Now, the other thing that might happen Friday instead of that is I might jump over to differential equations world and do the partial differential equations next time. We'll see. But I guess I should stop here. As much as it's tempted to keep going since we We could. But I will stop. Let's see here. Thanks, guys.